I had a friend who was a professor at the University of New Mexico who I had worked with while at Argonne, and he was very encouraging and offered to take me in as his student at the university. So I went to work with him, and that person's name is Cleve Moeller. He was a professor there in the math department. I ultimately received a degree in applied mathematics from the University of New Mexico in Albuquerque, and then went back to Argonne and continued working there, and continued the development of mathematical software. Through the course of time, I had developed a package of software called Linpack. Linpack, many people think of Linpack as a benchmark, but it's actually a collection of mathematical software for solving problems in linear algebra. And that collection, I was interested in understanding how well it worked, and I put together a little timing routine which would basically evaluate the time taken to solve a certain problem. And I would run that on all the machines I had access to and built up a little table. And that table had maybe 20 machines initially. And over time, as I got access to other machines, I added to that table, and it started growing. As vendors came and wanted to sell us machines and telling us about the great capabilities that their machines were going to bring, I would pull out this program and ask them to run it, and then that would add more machines to this list. So after a while, that list had a life of its own. I generated a report, and many people found it interesting in terms of looking at the performance of machines and trying to understand how their system fit in, how it compared against some of the machines that we have today. That benchmark eventually was modified as the architectures changed, going from scalar to vector and then vector to parallel. But ultimately, it started through trying to understand how well software would run, numerical linear algebra software would run on these machines, and trying to understand what the weaknesses were with respect to the software or with respect to the machines, and trying to understand how we might improve either the software or other machines to ultimately make things run a lot better. This benchmark that's called the Top 500, of course, evolves from that particular benchmark. Back in 1991 or 92, a colleague of mine in Germany, Hans Moyer, who was a professor at Mannheim University, kept a list of the fastest computers. So he basically had collected a list of all the computers he knew about, and he was using that list as a comparison mechanism to say whose machine was faster than another's. But it was based on just a theoretical rate of execution, not an actual achieved rate of execution. So Hans approached me and said he'd like to use this benchmark together with the fastest machines to put together a list of the fastest computers. So that led us to developing this Top 500 list. So we have, since 1993, maintained this list of the 500 fastest computers running the same benchmark and looking at, in a historic sense, how things have changed, and perhaps looking at the architectures to understand what architectures are useful in terms of high-performance computing, which ones faded away over time because of their lack of generality with respect to scientific problems, and looking at perhaps some of the trends that we might expect in the future. So it provides a mechanism for extrapolation and looking at where the performance would be going over the next few years. So our high-performance computers are used in many ways to help in terms of our understanding of physical phenomena around us. We think about these high-performance systems as really, I think of them as telescopes in some sense. They provide insight that we wouldn't have through any other mechanism. They provide us ways to look at things that we couldn't look at, to carry out experiments where we couldn't carry out those experiments on a physical level. You know, we think about simulation, numerical simulation that takes place today for almost everything that we design and construct, and it provides us a way to quickly understand and to change the constraints that we have on certain problems. You know, thinking about something like simulating what happens when when an aircraft encounters a flock of geese, right? So that's an experiment that we hope we don't conduct very often. But we can do that experiment on a high-performance system, and high-performance computing system, and look at what happens as we change the parameters in terms of the number of geese, but also in terms of the design of that aircraft, and look at what we might do to prevent a catastrophic event from occurring. You know, one of the big concerns that we have today is, in order to move to those levels of improving 3 orders of magnitude, we will have to have some very fundamental changes take place in terms of the software that we use. And that software, I predict, is going to change in that radical, it will have to change in that radical way to effectively use the large number of processes that the machines will bring us. Our projections, say that by the year, let's say 2020, we will reach exascale systems, so 10 to the 18 floating point operations per second, and achieving that rate of execution will necessitate on the order of 1 billion threads of execution. So that means that our programming will have to be at a point where we can express algorithms and effectively use 1 billion things simultaneously in getting to our solution. And that's an incredible challenge today. Going to the next 10-year period, going to exascale, it's unclear how we would get there. And there are many challenges. Challenges from the software standpoint, trying to effectively express things, algorithmic challenges in terms of effectively using that large number, the class of applications which can effectively be placed in that way lead to challenges. There's many challenges with respect to the hardware side of this equation as well. Well, one of the things that inspire me and my group to conduct research is the great challenges that we have in terms of effective use of our high-performance systems, and trying to make our applications and our algorithms run more effectively on those systems. It's a challenging problem. It's one that requires a special insight and knowledge of the structure of the hardware, of the structure of the algorithms, of the structure of the underlying software, and trying to match the correct components to effectively extracting the potential performance that these machines have. Large numbers of processors require a different way of looking at how we effectively implement and schedule the operations. And many of these ideas have been looked at in the past, and by re-examining what was done there in the presence of today's large numbers of processors, we can effectively use them. That's just an example of how we're doing some of our work, but there's great challenges there, and those challenges really are quite demanding, and a number of us are looking at that as a way to make advances in the future.